Okay, welcome everyone to the Oxford seminar. This week we'll be hearing from Samuel George White, who'll be telling us about advancing human-machine interface systems through artificial intelligence.
Hello, everybody. I'm going to essentially discuss my PhD research so far. I'm currently in the second year. I'm in Anil Bharat's lab and co-supervised by Dario Farina. They're both at Imperial College London. Anil's background is heavily on computation with a bioengineering perspective, and Dario Farina focuses a lot on EMG, neurorehabilitation, prosthetics, that kind of bioengineering. So my background is in bioengineering, and recently have got a lot into computational work. My maths is definitely not as strong as everyone else here, so there's not too much maths in this, but and it's really an overview. So if there are any like specific questions where you want me to go into more detail, I can, but hopefully this is quite light and understandable. So yeah, my research is on advancing human-machine interface systems through AI. What these are, we interact with them a lot of the time. For example, your Apple Watch, or if you've seen like smart glasses that are coming out. Mine is focused specifically on the use of EMG wristbands, which are essentially like wristbands you can place on your wrist. They have electrodes around them, and you can pick up the electrical activity from your wrist muscle group. And the focus is for like AR, VR, and things like that. Okay, so essentially, to start from the basics, when you kind of first think about like sci-fi and stuff, you may think of that. I always think about Iron Man. So I feel like my whole PhD is like Iron Man, but behind the scenes, like what the audience doesn't get to see, and how we can kind of make those ideas and robotics practical and real. So on a note of specifically what I'm trying to work on, it's essentially a degree of freedoms game. Essentially, these are the kind of things we do want to be able to create that can actually help assist us with our day-to-day work functions. So power augmentation, essentially just creating a robotic device that can increase the strength of a person doing a task if it's lifting heavy machinery. Workstation augmentation, again, if it's, for example, things outside of their reach, can we create a system that can help them? Precision augmentation, for example, if someone's had an injury where they've lost the ability to write, typically like stroke victims, can we assist with that? And all of these things fall under degrees of freedom, degrees of freedom augmentation. So, or essentially we just want to add another control to our current existing bodies. I think that sums it up pretty cool. So yeah, some of the kind of applications that would more not necessarily be suited for industry, but it's kind of like people would like to see, or we've seen in films and things, but we want to see how real they can become, is of course robotics that can assist like medical practitioners. Then also, for example, someone in a wheelchair, if they just want simple assistance from their wheelchair, going beyond them being able to ride around, but they can actually have their wheelchair with extra arms, so to speak, be able to perform more functions and help assist them in their daily lives. Or imagine a pianist who, instead of only having to play with two hands, they could play with three. Imagine, some great music they may be able to create with that. And one that is most close to my study is essentially using peripheral muscle groups. So these are muscle groups around your arms and legs, which you can actually send signals to just through thought, and we can actually kind of harness those signals, pick them up, and try and use them to control external devices, i.e. a telephone, and that's kind of my specific research area, what I'm trying to get into. Yeah. Okay. Yeah. And that takes us into the kind of realm of bionics. So my supervisor, Dario Farina, he does a lot of work on bionics, which is simply if someone's lost a limb, can we give them an artificial limb that they can actually wear, or a prosthetic, and can it actually assist on their daily lives on a day-to-day and actually help them kind of not feel as less abled, but almost get to a point where they feel just as abled and even more so. And this is from Open Bionics, just a quick video showing kind of one of the state-of-the-art prosthetics and where we're currently at. So this lady lost both of her arms, but she's got the prosthetic on, and she's actually able to control the grip she provides to the bottle, the actual motion of lifting and tilting and being able to pour a glass of water and then being able to drink it. And of course, like for someone, if they had lost both their limbs, that is almost like, well, it's definitely life-changing to be able to get that kind of mobility back. So that's just, yeah, one video showing where we're currently at with this technology. And another, okay, I don't know how to get it to play with sound, and I'm not going to attempt to, but for example, if you can see, she's wearing a wristband with electrodes on it, and they've hooked it up to be able to, from essentially the spatial location of her arms and the electrical signals that are being sent through to her wrist groups, they can actually model what her arm looks like and what it's doing just from that alone. And then from that, you're able to control a robotic device. So for example, if you think of someone who had lost their hand, for example, those signals may still be getting sent to the forearm muscle group, which we can actually use to give them a prosthetic hand, pick up those signals and be able to perform as if the person didn't lose their hand. So this is a current also one state of the art of where we're kind of up to with this technology. So yeah, these are kind of high overviews, essentially where we're at and what my research focuses on. Then I will go a bit deeper into like what I'm looking at and where I'm currently at with my particular study. So yeah, my particular study is to create an interface that could, for example, replace the biological hand. And in this diagram, essentially, is just if someone had lost a limb, like from their arm down, could we actually pick up these same signals that are here, decode them using AI, and actually send those signals to a prosthetic that we give them and allow them to do their day-to-day function. So the typical process of how these things work, where we collect signals, is your brain would have a thought, for example, go in for a handshake. We don't even think about the fact we think about it, but it starts from the brain, it gets sent down through the spinal cord, through the muscle groups until your hand or arm lifts, contracts, and shakes. And finally, the final stage of that is reaching the muscle units. What we are looking to do is almost reverse engineer this problem. So essentially, we pick up these electrical signals from the muscle groups and we actually work backwards to kind of decode the brain's intent. And what that allows us to do is there's specific things where if we choose to think about doing certain movements, signals still get sent down. So I can think about shaking my hand without actually shaking my hand, and there's still a trigger process of signals that reach my peripheral muscle group. So we're looking at instances where we can pick up those signals, which are just thought, they're non-motion related, and can we use those to then control external devices? So someone can think, for example, move my arm to the left, and instead of them actually moving their arm to the left, we can pick up or recognize that specific signal and then use that to ideally control whichever device we would like. It's most beneficial in like a gaming situation like AR or VR. If someone's got the controllers in their hands and it has a wristband hooked up, they can actually create an extra degree of freedom. So instead of them having to move the joystick, say go right or go left, they can actually just think about that, and then their avatar in the game would be able to do that. That's like the ultimate goal, essentially.
So you're not like trying to simulate the actual action of the muscles, you're trying to reverse engineer, figure out what the intention was. And
exactly. That way we keep like an extra degree of freedom available. So if they do want to do whatever movement it is, they still can, also allowing us to use thought as an extra degree of freedom. So, yeah. So in my particular study, this is, okay, so there's two studies that I've done. This is One I'll just use to explain the kind of paradigm of my experiments and my data collection. But this was for a shin movement. So someone would sit down and essentially there'll be a force meter, which they're just pressing down, just flexing their ankle to see the strength. And we record the EMG signals from their leg. So I did that with 12 male participants, people from my lab really, and I recorded the EEG and EMG as they performed certain tasks. So the most interesting feature that I'm after is essentially, like I said, the thought things where someone isn't actually moving, but they're just thinking about doing a movement. How can we identify what those signals look like from a whole range of someone doing their normal everyday actions, jitters and things like that? So we have an experiment called a go, no-go paradigm, which is essentially for a wrist movement, for example, someone will just hold a steady force, and then on a computer screen, there will be a cue. It will say 3, 2, 1, go. And then after go, there would be like a ramp curve, which they'd have to follow. So they'd have to increase their force to go up and then slowly loosen their force to go back down. That would occur in a go trial. However, in a no-go trial, the computer screen would read 3, 2, 1, no-go. The person would, leading up to the cues, be preparing to do a movement, but as soon as they see no-go, instead of them actually performing the action, they cancel what they had prepared to do. So those are just the differences between the go and no-go trials. And on our EEMG recorders, this is what it would look like. So the orange lines are just the EMG signals offset for different channels. And what we have is like go and no-go regions. So for example, in a go region, this green dashed line is our trigger, which is when on the screen it either says go or no go. So we can see in a go signal, their force increases, producing the spike in their EMG as they're now contracting, and then that can go back down. Whereas in a no-go trial, they're preparing, they get that same trigger, but at the green dash line, when the trigger occurs, they see no-go, so they don't actually do any movement. But what is interesting for us to know, even though there's no spike here, like there is in the go trials, there is actually a change in a beta band frequency in their EMG range, and that's what we're kind of looking at to analyze. So in these no-go trials, what we have is cues that are dependent or relative to the trigger. So for example, this green band is -1 to 0 seconds relative to the trigger, and we can call that preparation. The person's 1 second away from seeing the cue, which either says you're going to do the movement or you're not. And in that time, we can say the signals that are produced there are preparation signals. We have our baseline signals, which is really anything prior to that 1 second beforehand trigger warning. And then after that, we have a movement cancellation phase, which is as soon as they see no-go, meaning don't perform any movement, but cancel and go back to rest state, that's our cancellation period. Does that make sense? Or is that clear? Okay. So what I'm then doing is looking at these different regions, the baseline, the movement preparation, and the cancellation, because essentially, in these specific times, someone isn't actually moving. It's all just physiological signals that are being sent down. And I want to actually train my AI to be able to detect what these changes look like. So, yeah. Just a bit about my pipeline process for the whole thing before I get onto like how I actually then train my AI model. So first it's segmenting the data. So it's essentially chopping it up into these colored regions for the no-go trials, then channel reduction, so using principal component analysis, I'm just looking at the most informative channels. So if I have a wrist electrode with either 64 or 128 channels, not all 128 of them are going to be giving me useful information. To help my model train better, I'm essentially just finding which ones produce the most informative readings. So yeah, PCA. Then filtering and normalizing. Again, there's a specific beta band range that we're interested in because that correlates to a similar frequency that stems from the brain when someone's thinking about doing a certain action. So I'm filtering, specifically honing on that frequency, and then also distinguishing between below that frequency that frequency range and above. And also there's downsampling and normalization. And then there's to kind of increase the robustness of my model, some data augmentation. I may increase some noise. I may kind of offset it by a certain time position just so I can get my model to actually be able to adapt for real scenarios on a day-to-day basis. And yeah, that's essentially the whole process of pre-processing.
So the shape bit, is this like telling you how many like elements are in each type of?
Yeah. So this would be, for example, 7 participants. Oh, yeah. 7 participants. The classes I'm looking at, so whether it's preparation, baseline, or cancellation. X would be the total number of trials I have. 2048 is the sampling frequency for 1 second, essentially, of signal. And then 64 is the number of channels I decide to use. And of course, I've played around with these a lot. I've sometimes included more channels, included less, used all my participants, but that was a big mistake. And different things like that. But yeah.
And like, does figuring out how to do these like sort of simplifications of the data, like, is that informed based on the results you then get when you train?
Yes. Okay. Yeah. So through a lot of back and forth, kind of, this was one that I almost treated like a baseline or something that I could actually build like better results off of. Everything else wasn't always great, unfortunately. But yeah, I guess that's the PhD. My supervisor kept saying, yeah, you're meant to get it wrong a lot of times. Yeah. So we got there in the end, and I have here it is. So for example, this is what one of my architectures. So this is just a classifier network, essentially, where I can put all of these signals in my 1 second baseline samples, my preparation and my cancellation. And for example, the output of this particular model may just have 3 nodes where it says 0 baseline, 0 preparation, 1 cancellation. If it strongly feels that this signal you've inputted reflects a cancellation phase. And yeah, so this is a simple classifier architecture. I guess technically it could be referred to as like using deep learning, but this isn't very complex at all. So it allows me not to, when I tried it with more complex models, there was a lot of overfitting, and because my data set is so small, I just thought it's best to not try and do that because the model will just keep doing too much. So this is kind of like my baseline architecture of what I had. And in this particular case, because I had corresponding EEG data, I could input both my EEG and EMG so that I kind of was probing it to look at the similarities in the frequency changes in a certain beta band range, because that would help it to actually know, oh, that's what we're trying to find. Especially with these classifier architectures, I've learned you have to almost make it abundantly clear what you want the model to do. Otherwise, it will take the easiest route to learn something. I think one time I had a participant who essentially it just memorized how many samples before the participant typically actually did a movement, and it used that to actually learn, which of course may be great results for that one participant. The moment you give it to someone else who has a slightly faster reaction time or different reaction time, or the electrodes are just placed, it is terrible again. So yeah, that was like one of my baseline models. Then
so the final like output dense to, what's that?
So if I start from, I'll have 9. So I'm trying to get this to fit into 3 nodes, for example, from my first 2 inputs. Mm-hmm. So I would have 15 channels in this case by 1,000, and then my sampling rate, which could be 2048. That's my EEG, my EMG, same thing, but only 8 channels 64 channels reduced to 8 channels through PCA. And it's going from all of these channels to reduce it just to 3. So my penultimate layer, just after my dropout, has 9 nodes. Mm-hmm. And then the final dense layer reduces that to 3, where each one corresponds to like the baseline, preparation, or cancellation.
Okay, cool. And EEGs versus EMG, are these like both, or how are they different? Like, do you expect to get much better results if you use both of them, or?
Yeah, you expect to, simply because you're feeding it more information. So if it is able to identify what the pattern is between the two, if you're giving it more information, it will be able to do a better job. EEG is just the recordings for the electrical activity from the head, and EMG is from the specific muscle group that I'm looking at. If I try and zoom back as quickly. So here, for example, this cap has a bunch of, so that's the EEG when it's recorded, and then on the leg is the EMG. So recording both and obviously setting them up so that in time, it's it's essentially meant to help my model. This paper by a lady in my lab, it showed that there's a synchronicity between the EEG and the EMG in a certain frequency range when someone is just thinking about doing a certain movement. So my thoughts was if I feed it both and it's able to detect that kind of synchronicity, it will be able to do better if it receives both inputs. Yeah. So from that architecture, these are kind of my early results that were the first set of results I was happy with, trusting. Of course, a lot of back and forth and changing, tweaking, and optimizing. And what this is essentially, so I can have a 2-class average versus a 3-class. My 2-class is instead of including my baseline signals, which is when the participant's not doing anything, I discard that and I only focus on my preparation and cancellation. How well can it distinguish between the two? Because if we're able to actually get it to do that, naturally, if it's able to identify, okay, you're preparing for a movement, or you've just cancelled a movement, anything to do with baseline should essentially not be recorded as anything. It wouldn't recognize that as preparation or cancellation. Versus my 3-class average, which is essentially when I do also include random selections of baseline to see how well it performs against the two. So unfortunately, the beta band range in a preparation phase versus when someone is just barely doing any movement, they are very, very similar. So that's why there's a drop in accuracy. It's very hard for my model to distinguish between baseline and preparation because they're very similar, and there's not much of a change in that frequency range. However, in the cancellation, that's where you see like a huge jump. So that's why it performs so much better when it's just asked to distinguish cancellation from preparation. Yeah. So initial accuracy results, and then my loss results as well from training the model. And these are over 5 different splits of my data. Yeah. And then moving on to analysis, I will try to get through this quick. Of course, a lot of text, but one essential library I used to kind of see how well my model was doing and if it was actually learning was GradCAM, which just allows you to visualize the model's kind of weightings throughout my CNN structure to see what parts of the input signal is paying the most attention to. And this is for an earlier on data set where I had more classes. So in this case, I had classes like my baseline, but I was also trying to distinguish between the type of movement the person was doing. So whether they're extending their arm or they are flexing. And then there's a bit that I won't get into, but it's related to an error, which is if they felt an error, they would essentially squeeze a board to kind of dictate, okay, yeah, I've detected an error. I'll skip past that for now. It's not too important, but this is essentially showing these are the different EEG channels, and it shows for different classes which channels it paid the most attention to. So for example, if someone is extending, you can see that channel C4 on the electrode and CP3 would be the one it pays most attention to. Whereas when errors like this one, movement after squeezing, which I was most, was this one? Oh no, sorry, squeezed without error. And yeah, ignore that. It focused more CZ and C1 and C2, which I was actually happy with because my supervisor said, yeah, that's what it should. So if your model is doing that, I guess you're on the right tracks.
And it's also like telling you what you should do when they're filtering or something, like if it's not paying attention to it.
Yeah, exactly. So when I first did this, it was almost like all blurred, or there was like random. You couldn't see specific channels being. But as you begin to tweak it, then yeah, it's like an iterative process, and then so that influenced my filtering, and then also some channels I just discarded altogether because they were either too similar, so there was like no difference between them, so I could just discard them so it can focus more heavily. And then also I could add like attention to my model architecture so it focuses on specific channels that I know are informative. This is a lot, so essentially following on from all of those things, there's a lot of adjustments I had to make because my supervisor wanted to push us to get to like, okay, will this now work in a real-time scenario? So it's great when I've done the experiments, I've collected the data, and I'm just training it offline, but does it work online? And in order to do so, what things do I need to change to improve my model to do that? So this is what I'm currently working on now. But okay, and this is just to help where I'm going make a bit more sense. So if you remembered before, initially I started with 3 classes, which is baseline, preparation, and cancellation. Because of where I obtained this data set for, in order to kind of tweak it to fit my go, no go paradigm, what they did is where I would have a trigger, they had an error essentially. And if a person was doing a particular movement and they felt an error, they would squeeze a ball to indicate an error's been present. And how I kind of tweaked it is if they felt an error, that's either like a cue for them to do a movement, or if there was no error at all, they would still be ready to, but they wouldn't actually squeeze the ball. So I kind of adapted this data set to kind of fit my criteria. And essentially these are the classes I was investigating in this like real life scenario. Again, we have baseline, flexion, if someone's flexing or if they're extending, then there's these different classes which are all relevant to the error. And the one I was most interested in is the movement after error, which kind of corresponds to a cancellation signal. So they're about to do a movement, but they don't actually execute it just yet. So those are the classes anyway. And what that allowed me to do is move on to like a sliding window analysis. And as scary as this looks, it's not extremely scary, but what it is essentially, all of these curves at the bottom here are color coordinated for the different classes that were present. And essentially it's just predicting motion happening, then I'd expect the flexion curve to peak and then drop after. If it's an extension, the same. As an error approaches, I'd expect the other signals to also peak and so on and so forth. That was obviously if my model was perfect, which is very far from. But in a slightly more detailed view, for example, this is how I was trying to get it to work. So to see how well my model could perform in real time. And to be honest, right now, it's not performing the greatest just because of there's so much differences between subjects that I'm training on, but then literally the slightest changement of the placement of my electrodes, it's almost like I'd have to train a whole different architecture on that. So it's now my work is how can I actually get this to do well in real time for different participants. And one of the best approaches would obviously be, train it on a wide range, like thousands of different people, because by that time it could have seen everything and it would still be able to make good adjustments. I can't do that. My lab's not big enough to find like 1,000 people to do it. But another approach that was in the slides before is actually make my model more compact. And there's a paper actually I'm currently working through, but I think everyone here will probably understand it a lot better than me. But someone else had an approach of essentially you can create a set of eigenvalues and eigenfunctions, which the eigenfunctions allow you to actually investigate what part of your signal are most important to a certain class or a certain action that's happening. And I think it was the eigenvectors actually worked in a way where it allowed you to distinguish between different participants. So for example, it was able to cluster, okay, these participants in a feature space, you can put them here, another participant you can put here, and you could actually see as you spread the two out, or for example, if two are clustered near each other, but there's still enough of a distinction between them, you can, or the model would know how to respond or react to one participant, just if they're going to be closer to another. So it allowed like a 3D separation, which is currently what I'm trying to adapt to my model, which is very, very difficult and technical, but essentially it's just a way to actually help my model be able to perform in real life scenarios, because it's no longer about if you see a certain signal, how well can you predict it? It's can you see a wide range of signals and still be able to do what you need it to do at a high level, which is pretty challenging. But yeah.
So I've got a question about sliding window, temporal analysis of sliding window. I don't really know what that means as well. Okay. So have you got like a static, like a neural network you've created, and now you've just got like trajectories of all these signals you're measuring like over sliding windows of time, literally. And then each time it produces...
Exactly, okay. Exactly. So that's just to simulate how it would perform in real time. So
is it not like, I guess the other piece of information, if you've got a trajectory that you might use, is like maybe you know that if you were previously in like a preparing phase and your next phase is has a high probability of...
Yeah, so these dashed lines should essentially tell you what phase of what's essentially happening, if that answers the question. So this is different to before when it was just a simple trigger, different data set, but essentially it can tell when an error is introduced or when a ball was squeezed. And for these class, essentially I should be able to determine, okay, this is the specific phase someone's in.
Okay. Is it like ever using the fact that it knew it was previously in an extension phase to like infer how likely it is to now be in an, like, it seems like there's extra data you could use if you've got a trajectory rather than just looking at the pieces.
No, it doesn't particularly do that, because, for example, I would have trained my model and then what I'm literally putting in is one time snapshot of the signal at that moment in time. However, because I'm using an overlap, so there's about a 60% overlap, it's like I can have one signal, at least 60% of the next signal that I'm putting in is still present in the one before. So over time, it should be able to kind of make adjustments to know. But yeah, it's not implicitly told we've just left this phase, anticipate this phase kind of thing. But yeah, so this sliding window is just, I would take a snapshot of my whole recording of my EMG, and over time, just fill that into my model and ask it to make predictions at each time. And then when it does that, I would just join all the predictions up into curves, and then that's what produces this kind of thing. Heavily smoothed and...
I was gonna say, these curves like curves of best fit, or is it literally just like smooth versions?
Best fit, just through spleen curves. And this is kind of where I'm at, or where I got to, and kind of my direction moving forward. So on first principles, the idea that whether this was even possible or not, the whole premise of it is to create a neural interface or some sort of HMI system that is non-invasive. I don't have to develop a chip, stick it into the brain, use Bluetooth or wireless technology to then directly control an external device. Can we do that non-invasively, just using different muscle groups in this case? Does it work? Is it even feasible? So the first stage of that was actually proving, yes, it was, and writing up about that. Then the second so what can we do with that? If we know that there's a potential area of success here, what can we move on to, or what could that lead on to, the implications of it? And then the third is kind of like what I want to focus on specifically to get my work up to scratch where it could work in actual real-time scenarios, to the point where it works generally. If someone were to buy this from a shop, they can train it once or calibrate it once, and even if the electrodes shift from one day they put it on to the next day they put it on, or even if they grow hair on their arms, which inevitably they will, can it still perform at a good level to know, okay, when someone's producing a signal like this is exactly what it's going to look at. But yeah, just improving the robustness and real-time scenarios of my model. That's where I'm currently at. My mouth is extremely dry right now, but I hope that was kind of cool. If obviously I know I got a bit technical towards the end. I guess just remember the early on slides with the cool arms extended. That's yeah. This is like Iron Man behind the scenes. How to actually get something to work, like to actually get an arm on and to be able to control it. There's a lot that goes into it, and then to use that to control something else. Very tedious, but there is feasibility for it. And yeah, my work is looking at how we can actually transform that from the idea stage to actually something that people could buy and use one day. So yeah, thank you.
Any questions?
So I was wondering, what is your best bet so far as to what is actually going on when you go from like the preparation phase to actually doing an action?
Mm-hmm.
Does the brain send a specific go signal, or does it suppress a signal?
Yeah.
And I guess, is it the same, if it's a go signal, is it the same go signal for any movements? Or is it a different go signal for each leg?
Okay, yeah. This is me making an educated guess. But for different go signals, someone is expected to follow a curved path when they see go on the screen, and that path is the same each time. But of course, no one's going to be perfect accuracy following a curve on the screen. So overall, it's like the envelope of that go signal, the spike when they've actually started contracting, you can see similarities in that. But of course, it's actually very different if you like zoom in on a smaller scale in each go trial. And then in terms of like the thought process behind actually when you see go performing the movement and moving from the preparation phase into the go phase or execution phase, yes, that you can see a change in from the signal being sent from the brain to your muscle groups, like something has actually changed. For us, when we do certain movements, it's just so rapid we wouldn't even notice it. But if you were to take like a snapshot and actually very small, you can see very minute changes, and that's kind of what I'm trying to focus my model on.
One thing I was wondering is, have you guys ever plugged like an EMG onto someone who sleepwalks and try to see like if you get the same sort of?
I personally haven't. I wouldn't put it past some of my lab mates to try that.
Because I think it could be interesting, because you either should learn something about the process or something about sleepwalking. Either way, it would be an interesting thing to learn, right?
That's actually a good shout. I haven't done that, but that's something I guess we could do. Huh.
So how does so you showed some of the videos at the beginning of like current prosthetics and how they exist, and like I don't know how prosthetics work generally. So like what is the or like these types of prosthetics, like how do these work compared to how what you're suggesting works, right?
So yes. Well, okay, so long slides. So for example, this one, which I guess they would actually develop this model that is on the screen behind the lady doing it. That works in a similar way to what I'm looking at. So it actually does take the EMG signals, but on top of that, it measures like spatial dimensions of it. So specifically for this type, it collects more information than what I'm currently able to do. But yeah, for this one, this is about pressure sensors. So I think at the base of her arm, she didn't lose exactly from her elbow down. So there are still signals that around where like almost the stump of her arm is that can actually still get sent down. And I believe in this one they're using that, but also pressure sensors. So actually
Muscles are actually moving.
exactly. Is really there's a huge difference between someone losing the remainder of their arm from here to actually here, because a lot of the bulk that sends a lot of signals down is here. So she can obviously still rotate and things herself, but it's pressure sensor when it comes to actually squeezing the bottle and squeezing the glass that she's actually able to tense, and then the prosthetic can actually feel and react to that. Yeah, but it's still very cool. Yeah.
I have a question, maybe this is sort of beyond the scope of what you're looking at, but like assuming you've got a reliable model which can detect people's intention when they want to do something, and then you hook it up to like some robot that implements it, do you then get some like weird feedback situation where like once someone learns how the prosthetic works, when they want it to do something, they're now sending different signals like than what they would like can we like voluntarily send a like cease signal if we don't think that's the behavior it's going to perform, or like do weird things happen when actually the like EMG signals are controlling something? Do we then like modulate those signals to in response to what we then see happening?
So is a question like for example, if someone thinks about cancelling a movement, if we extract that to do something, does that change when they actually do want to cancel a movement and not think about it, how that would work?
Yeah.
I haven't actually thought about that until I've actually linked it to a prosthetic and stuck it on.
Or just like, is it important that the actual intended consequence corresponds to like the original intention someone would have if they actually, you know, had the muscles to move? Like, can someone learn to associate? Like, could you find some signal that's easier to detect than a C signal and have it do the behavior you want rather than trying to analogously?
Yeah, I'm sure there is. I know from myself, it was my supervisor who suggested this particular approach looking at preparation and cancellation because he had prior study done in that. And it's not, these aren't like, our brain doesn't think of movement in a term of, okay, I'm at rest, now I'm about to prepare, now I'm about to count. It just like, it does it in a way where it's like, okay, this is the end goal. What muscles, what fibers need to contract in order to be able to do a certain thing. In terms of the bit about will it be a loop where it changes? That's an interesting thought. I'm not going to say I'm 100% sure, but I do think, for example, if we use the cancellation state where someone just thinks about stopping a movement, how it was trained is those are specifically in no-go states. So prior to it, the person wasn't performing any action. Whereas if someone is like in a real life scenario and then they still think, okay, stop the movement, the hope would be that, okay, the signals would be different between a cancellation state in a go case where they are moving and a no-go case where they're not. But that's something I can actually explore. The reason I guess I didn't is because if someone is performing a movement and then they think to cancel it after, that's like a go phase, which is different to like a no-go phase. If that makes sense. That's an interesting thought. But yeah, that's obviously hoping that it goes well enough to the point where we can actually get really good and reproducible results. I forgot where it was, where someone said it, but just comparing invasive and non-invasive methods. Someone said an invasive, so me trying to essentially understand and detect and know exactly what the intent was just from reading EMG signals is the equivalent of putting a microphone in a football stadium and trying to isolate like one particular part of the arena's conversation. The noise level is so much that it's a huge challenge. That's comparing it with invasive, where if I just wanted, I could stick electrodes directly under the skin and onto the muscle groups. And that's where the most challenging bits arise because, for example, in one case, I can do as much pre-processing as I'd like to kind of beef up and show my model, this is what I'm interested in focusing in. But the minute someone moves and the electrodes shift by a tiny bit, yeah, it's like you have to almost start again. So that's the main problem that I'm trying to overcome.
Yeah, it's amazing to me that you get anything at all from like EEG readings, because I would have, like, at least here I'm like, yeah, probably most of the electrical signals in my arm are to do with my arm.
Yeah.
But like stuff in my brain,
Yeah.
when I'm just like, brains do loads all the time. So it's crazy that there's any, like you're saying in this paper you studied, like the fact that there's any sort of frequency between the two is pretty, like, that's really surprising.
Okay.
Like, that's cool.
Yeah, I'm lucky. I didn't have to worry too much about that. But I can send the paper from her name's Blanca. I think she's in America now actually. But where she did the study, and I think there was a lot of isolation she had to do. I think there were so many. When I did experiments, this is just for muscle groups, like a subject wasn't allowed to drink coffee in the morning because it would affect, their jitter rate, how much they jitter, how much they move, and even their reaction times. And I know she did a lot more like control measures. She had a lot more in place to kind of just isolate what she wanted. So yeah, I guess if I find that paper, I can send it, and then you can see what, because it is true. Yeah, it's difficult to focus specifically when the brain is doing so much.
Actually, now that you mention it, how hard do you think it would be, at least theoretically, to suppress signals?
In what way?
So we know that you're getting these signals that you can read through the EMG. If you were to try and prevent those signals from like say the goal signal from actually reaching where it's supposed to reach, would that be possible?
So,
because I don't know if that's what's going on, but I was wondering if it could help with something like Parkinson's disease or something like that. Like unintended movement be suppressed.
I don't honestly know.
Like maybe, I don't know if this is possible, but I was thinking like, maybe you get a bunch of signals, and I don't know if that's what's happening with Parkinson, but maybe there are signals being sent that shouldn't, or something like that.
Yeah.
Would an AI be able to distinguish between what are like the good signals, like the conventional signals, and the sort of jittery signals, and just block out the jittery ones?
I think an AI could.
Seems like if you struggle with noise in like a super controlled environment where they're not even allowed to drink coffee, then struggling with like the noise distinction where the signals are like large enough that jitters are like this, it seems.
That would be an extremely difficult problem. And then also thinking about how an AI would then even be able to inhibit those like reflexes or something in a Parkinson's case would be very
I've seen there is difficult. Like small brain implants for Parkinson's, right, that reduce jitters. They do some frequency and you turn it on, and there's pretty incredible videos.
I think I've seen
very invasive like operations.
I had seen something similar, but instead of trying to work on the signals, instead it was like some sort of strap that you wore. And it would like actually detect the motions themselves.
And like actually did correct. Okay, this was I saw a brain thing happen. I was playing a guitar with one. Yeah.
Another question. So you talked about this process of like you've got a bunch of channels and then you filter them for the ones that matter, and you can sort of see on the images like the things that light up are maybe important. Like how formal are the methods you use to do that? Do you just like look at it and say this is clearly important, or do you have some like algorithm for reducing the dimension of?
When I make an act.
Oh wow! Now this. So I think for the second part, so this is actually a library that essentially once I've trained, so it's not me looking and deciding what is most important. After I've trained my model, this particular library, GradCAM, essentially looks at certain nodes or activations which I can then remap to kind of suggest which channels were you looking at. For example, if I get to a layer in my model where it's ideally a one-to-one relation between nodes and channels, if there's 64 nodes and I see maybe nodes 1 through 3 have a significantly higher value, whereas the remaining nodes or however many others don't, meaning that, for example, I can feed any number of things to the remaining nodes and it doesn't affect what the model predicts. Whereas if I change just one of these highly activated nodes by a slight amount, it could completely shift. Then I'm able to kind of remap that to see, okay, which channels actually are influencing the most. And then that's how I got kind of these. So these are actually spectra of my initial data, just rewrapped into the shape of my channel, so you could actually see which parts of it light up the most for certain tasks. So yeah, it wasn't me eyeballing it and saying, yeah. It's too, yeah, I mean, when it starts like that, you can't tell anything, really.
Right.
Like, yeah.
But like at that point where you've got the spectrograph, are you then like eyeballing it, or what,
Yeah, these are just again, it's not, I'm like, for example, I don't use these to kind of point into a specific thing. This is like an analysis method for me after to say, okay, is that in alignment with what we would expect in the first place? For example, if it's to do with someone doing a movement and I've got an EEG from everywhere, I'm expecting the motor cortex to light up more than any other part of the brain. If it's not, then I'd assume, okay, something's gone a bit wrong. So these are kind of like just checks in line with that. Yeah, that answers.
And also used.
Essentially, I'm not eyeballing that.
Can I ask?
Yeah.
Yeah, I'm sorry. Yeah, I'm really interested with your data. So yeah, I'm not sure. Maybe I have several questions. What kind of data structure of your database? So for all the collected data, what does the data structure looks like for raw data?
So I would have, for example, a MATLAB file, which is pretty large in that I would have, where's my experiment? So in this case, for example, I would have a MATLAB file, 12 different participants.
Okay.
And then for each participant, I would have the actual data itself, which is a huge 1D domain of like time signals. And then however many channels there are, usually it's like 2, 5, 6, or depending on the experiment, I'd have that. Then I'd also have my trigger times, which tells me when the cue, for example, on the computer screen showed either go or no go. Then I would have like a states vector, which essentially tells you, is this going to be a go or a no-go trial, essentially. And then I'd have some more, which are like kind of error scenarios. For example, if someone moved when they weren't supposed to in a no-go trial, and it's just letting me know to discard this trial because the participant made a mistake.
Okay.
Yeah, does that answer your question?
Yeah, thank you. So then, based on that data, it seemed to me, so since your machine learning algorithm, that's for classification, right? So so for example, in the machine learning algorithm, classification algorithm, what is the different classes and what are the features? So I'm confused. I've seen several like go, no go type classes.
So the so go and no go aren't particularly classes per se, but they're more like trials in the experiment. So in one experiment that could last a minute and a half to 2 minutes, there's going to be some go trials, some no go trials. So the participant is never confident that they're not going to have to move, otherwise that would then affect the signal we want to see. So the go and no go, they're not so much classes for my model. It's more because I'm interested in a cancellation movement. Since a cancellation movement can't happen in a go trial because they actually do move, the cancellation only exists in the no-go trials. What I can do is just chop these windows for just the no-go that I want. And then then these shaded regions are then actually what gets sent as my 1 second window. This is a 1 second window of a baseline class, 1 second window of a cancellation class. And I can feed that 1D time domain signal into my model with a label saying this is a cancellation. If you see something like this, there's a high chance it's a cancellation.
So the label is only, for example, I only have 3 labels, 1, 2, 3.
Yeah, for example, for one trial, I would have three windows for 3 different classes.
Okay.
Yeah.
Um,
That's for one trial out of someone, maybe in one recording, there would be about 20 different trials. Then a person would do maybe like 20 different 20 different recordings. And then there's multiple different people.
Yeah, I was thinking of the whole data feeding into the machine learning algorithm.
Yeah.
So it's like the data is like, to me, is I put all the participants' data and in the together. I will not separate different participants, and then I label those data by for example here baseline, cancel or something. So that is the label of my data, right?
Yeah.
And those label is the classes for my classification. Okay. Oh, that's really helpful. So
if this helps, for example, so in one approach where if we just take this case here, if I ignore my beta powered branch, but I just fed this into my model, what this would look like is the first argument is just the number of participants. So in this case, I only chose 7 of my participants.
Okay.
Then there's still only 3 classes, my baseline, cancellation, preparation. X would be the actual total number of individual 1-second windows that I have. So that often goes into the thousands. And then 512 is just the number of time steps in each window. And 16 is the number of channels or electrodes that are actually going to get fed into it. So when it actually comes to training, it does get told, okay, if the first index is index 0 or index 1 through to 7, it knows it's a different person, essentially. So even though the class is the same, it knows it's a different person, but it's meant to ideally learn that even though they're different people, these signals all represent the same cancellation class or whichever class. And that's how it's meant to learn how to differentiate classes as opposed to differentiating participants. If that makes sense.
Different participants and also different classes.
Yeah, so meaning I should be able to give my model a cancellation window from participant A and a cancellation from participant B, and it should still be able to identify that, okay, yeah, these are both cancellation windows. It shouldn't struggle with the fact that, because the participants are different, it can't identify what cancellation looks like. But that's a huge struggle because I'm
not sure how that works, but it seems to me very cool.
Yeah.
Then I'm not sure I'm not quite familiar with the CNN, or I'm not sure if that's your algorithm.
Yeah.
So I'm not sure for your algorithm, would you manually to say what's the different features to fit in the algorithm to have the algorithm to classify or no? It is the algorithm automatically is like, I just feed my data there to the algorithm. I do not just need to specify features.
It's a bit of both. So for example, I can, so this is my early on architecture where I didn't add things like attention, or my kernel filters were just almost randomized. But essentially, as I made more and more iterations, I could choose a kernel size that I know is going to focus on a specific frequency range. Okay. So I can start with a baseline architecture where it does everything and I just hope for the best. Then I can look at how the architecture performed after, and then I can say, okay, if I want you to focus on a 13 to 30 hertz frequency range, then I can select a specific kernel size, which actually almost like downsamples my input signals, but preserving that frequency range. So it almost forces the architecture to kind of learn features in that frequency range, but kind of discard everything else.
So does the algorithm automatically learn the features? It's not say I manually say this is the features.
No, that's what I mean. It's like a bit of both. It's going to learn, yeah, it's going, like I can tweak the architecture so that I know mathematically it's going to focus on these kind of things. Or like I can add a spatial attention mechanism, which means like I'm telling it, okay, in this specific time frequency range, this is how you will know if something is going to happen or not. And this, essentially, this is going to be a key factor in deciding what class this falls under. So I can like kind of probe it to know or what to look out for. But at the end of the day, I'm just feeding in the data and like hoping, like kind of like the black box mystery, hoping that it does what I've pointed it to do. But again, if I don't do a good enough job of that, it will learn a complete random factor that I didn't want it to, and then make predictions based off of that instead.
Yeah, this is my point. It's like, so you see, if I have 3 classes, its accuracy is very low. My question is like, can I find some features which can separate that very more clearly? If I find more clear feature, maybe I can improve the accuracy much.
Yeah, but
It's hard, right?
yeah, that's the hard bit, and that's the bit which is like essentially how detailed are you going to go in telling the model this is exactly what I want you to look for, because it's like I can maybe identify one rule and say, okay, yeah, this frequency range is very informative in helping you make a decision. The model, so distinguishing between different classes, but I can't do that for every specific case, because, for example, for one person, a frequency range of interest may be 25 to 27 hertz, whereas someone else, it may be 23 to 25 hertz. I can keep it broad and hope that my model learns, okay, if it's this participant, it's a slightly higher frequency range or a slightly lower frequency range, but I can't kind of go any more. Otherwise, it's just me labeling every single data set.
Like if you knew what to look for, you wouldn't.
I wouldn't need that,
Like,
exactly.
Like, I already know.
Exactly.
I see, yeah. Okay, so, yeah, I'm quickly, yeah. So then I think although you have temporal data, it's not like, so the data feeding into the model is not a time series, right? It's like time segments, just the behavior of each time segments, what that is. So
it's like a what is that? It's more of a snapshot so I can take a snapshot of a 1 second window, and if I'm just taking my top channel, this red one at the top, it's going to be the time step at each point over 1 second, and then a channel down, it will be the next one.
Oh, so okay.
So it is a time domain 1 second window that gets fed in.
So that still seems to me like not time series. It's just discrete data points or something.
It is, so in this case, for like offline actually training it, it's discrete. I'm gonna take the specific snapshots kind of relative to when the trigger occurred, so it knows, okay, if you see a similar envelope to this kind of shape, this is the phase that the person's in. But then also what I do is, for example, within a 1 second window, I'm gonna have different like overlaps. So it will see essentially maybe like a 3 second window in total, but it receives it as 1 second snapshots with slight overlap over one another.
Okay.
That makes sense.
Yeah. Can I ask what is the size of your database, or the size of your data?
As in the number of people, or
no, it's like how many
gigabytes?
Sorry, I'm not sure. Or roughly, I just want to have a sense
I can try. I'm just gonna have to look.
Sorry. Because it seems to me it's not that small size. Maybe it's big.
What? I mean, I don't know what is big or small.
I'm sorry. Yeah. I didn't do much deep learning, so maybe for traditional machine learning algorithms, maybe that's big.
So after I've processed it and everything, it's 10 gigabytes.
Oh, 10 gigabytes.
Yeah, and that's
numbers.
yeah.
I was expecting like some number of hundreds of megabytes.
No. It's
Okay,
yeah.
I guess
It's
it's because even at like 512 hertz, it's like there's
it's a
lot.
lot. Yeah.
Okay, yeah. And
It's
16,
yeah.
Okay, yeah. But still.
Yeah, it's a lot of channels as well. And then if I add augmentations like slight time shiftings, that's basically doubled one thing. So yeah.
So a little bit my final. Do I have time?
Sure,
Maybe
one more
no.
question.
Okay, yeah, sorry. Oh, wow. Okay, I have two.
I mean, one more and then I'll stop the recording and then.
We're recording. Okay. Sorry. Can you see more details in your data pre-processing? I can understand the PCA for dimensionalize. Yeah, then you have to filtering and then have add random noise. What is kind of the reason, and just can you tell more about that?
Yes. So maybe this is kind of everything. And again, my approach has changed over time. For example, there was a time when I moved from doing time domain to like spectra domain instead. But over quite a few different iterations, I kind of got to my first stage is always going to be filtering and normalization. I know above a certain frequency range, those EMG signals are not going to be relevant for anything or for my study particularly. So I'll just apply like a band pass filter to kind of stay in range of what I know I'm going to want. That makes sense? Yeah. And then initially my signals were recorded at 2048 hertz per 2048 time steps per second. That's just too big for my model. Like it didn't need to be so detailed, so I could just downsample it. So it's a bit easier for me to like move my data. I have to train it on like my university cluster. If it's 2048, that's like every data point is 4 times as big size wise to move. So I just downsampled it and preserved the same features. Then amplitude and z-score normalization. It's actually just making sure that for a certain range or for each participant, each signal is not necessarily maximized, but relative to each other, it's essentially visible, if that makes so.
I think I kind of get that. It's just like you filtering the HD range based on your interests.
Based on what I'm interested in. Yeah, exactly.
Then why you add one random noise to enlarge the difference?
No, that is so my model doesn't memorize just what. So for example, if I take a snapshot of a signal that I fed into my model, because it's relatively a small data set, it's just about 10 participants. In some cases, I trim it down to 7. With a complex architecture, it's so quick to just memorize exactly. So it can, if I give it one signal, it can memorize that. But even if I just add 1 to every time step in that signal and I fed it in again, it wouldn't even be able to. It's like this is a new signal altogether. So this jittering and adding random noise is just so it can still know, okay, even if it's a clean signal versus a signal that follows the exact same envelope, it's just a bit more sporadic or fluctuating in its shape, it should still be able to recognize, okay, these are both belonging to the same class. So it helps it get more robust. So that's just why I did that. Yeah.
Yeah, so to avoid overfitting.
Exactly. Yeah.
I see.
Yeah.
Thank you so much.
That's cool.
Yeah.
Pleasure.
Okay, let's all thank Samuel again.